Assalamu alaikum wa rahmatullahi wa barakatuh. Today we will discuss about design of pattern for metal casting process. Now metal casting is a very important process because there are many cases where we can't avoid to fabricate a component other than metal casting. For example, a hub of an automobile cylinder. You can see the picture over here. However, this uh, metal casting, primarily the initial and basic principle is by having a route through sand molding or sand mold casting. Here is a cross-sectional view of a mold. The flask is having two components. The lower one is known as drag, the upper one is known as cope cope, and this is the required component. Okay, now it is filled with sand, and therefore we want to make this cavity. This cavity is to be made in the sand mold, and therefore now we have to design a pattern such that the cavity obtained can give the required product. Now there is a step of metal casting. If you look, then first one is pattern making, then core making, molding, melting and pouring, shakeout, fettling. And if we look into the how the sand recycles, therefore this flow chart shows how the sand and the metal flow takes place. Now the sand from sand molding is being done. Now after molding, pouring is to be done in the mold, and it is allowed to cool. Then the product is shaked out, and unnecessary they are to be cleaned, and unnecessary part is to be chopped off, finishing, and then product and waste they are finished, and they are chopped off, and they are ready to recycle. Now therefore, after fettling, the sand and the sand is to be the metal is to be recycled, trimming off the unnecessary remakes. Products now they are to be taken out, and they are again melted and being recycled. Similarly, if we look into, then the flow of the sand can be given by this figure. Shakeout gives the product, and the sand is allowed to cool, and then it is being processed so that it becomes moldable, and then sand is mixed. If there is a loss of sand, unnecessarily undesired sand is to be replaced by, and therefore they are mixed, and then the molding is to be done. And this is how the molding, the recycling of the sand takes place. Now therefore, to have the cavity in the mold, we need a pattern. Now there are different types of patterns, like single piece or solid pattern, can be a loose or split pattern, can be a gated pattern, a mash plate pattern, cope and drag pattern, sweep pattern, skeleton pattern, and master pattern. Now this is a single piece. This is the product that we need, and therefore it is made in one and a single piece, and therefore we call it a single piece pattern. This can be divided into two half, upper half and the lower half, and therefore it is known as two-piece pattern. And if it is specified which half go to which flask, and accordingly we name it. We can call it the upper half, we say that it has to be assembled in the cope, and the lower half in the drag, and therefore cope and drag pattern, cope and drag pattern, and this cope and drag is being separated by a match plate so that they can be properly aligned. The two portions can be properly aligned, and therefore we provide a thin match plate, and therefore we call it a match plate pattern. Now, this is the actual product. This is the actual product. Now, to have this product, when we make a mold, we need to provide the passage from the top of the mold to the cavity, and therefore we need so many accessories: pouring basin, screw, runner, gate, and all that. And therefore we, instead of providing this passage separately, we make a pattern in which they are having all these accessories, so that we need not to make these passage while molding. Therefore, having all these accessories elements with the pattern is known as gated pattern, because they are having all the getting system with it, and therefore it simplifies and makes the molding process easy. Now, if the size of the pattern is very big and they are symmetrical, then instead of making the whole big pattern, we make a scraper blade pattern. Now we fill the mold box with the sand, and we rotate it about the axis. We rotate it about the axis and scrape out the undesired molding sand and have the cavity. Okay, and therefore this type of pattern is known as sweep pattern, because we sweep out, scrape out with the help of a scraper blade unnecessary sand, unnecessary molding sand. Therefore sweep pattern. And if it is, suppose you want to have a full pattern and it is a very big, therefore it will be weighty and it will be very difficult to mold and transport and have the mold. And therefore what we do, then we may, instead of we only looking for the final surfaces. Therefore what we do, that we make a skeleton. Instead of making a solid one, we make the skeleton of the pattern, and we cover the surface, the active surfaces, with the required surface finish. We make the active surface, and therefore this decreases the weight and easier to handle while molding. Therefore this is for big pieces, we make skeleton pattern. Now, what are the allowances? Because after molding, we will pour the metal. It will, of course, during solidification, shrinkage and so many other things happen. Therefore, what are the allowances which we need to incorporate in the pattern? Number one is the shrinkage allowance, because while metal solidify, the liquid shrink, there is a shrinkage in the phase change and also in solid form, and therefore that allowances, the shrinkage allowance is to be provided. Depends upon the metal, what is the pouring metal. Another thing, there is a certain location in the product where we need machining. Therefore sufficient amount is to be given in the metal itself, so that machining may be done, and therefore we give a machining allowance depending again upon pouring metal and molding technique, what technique we are adopting, how much machining we need, and that is the draft allowance. Now, for draft allowance, there is a vertical surface in the product. Now, if the vertical surface while molding, we have to take the pattern out. While taking out, the vertical surface will come in contact with the is in contact with the mold face. cavity interface, and therefore while taking out it may distort, it may erode the intersurface of the cavity, and therefore we need to give a draft, so that if we want to take that vertical surface out, if we want to take the pattern out of the mold, it may not erode the contact surface, and therefore a draft allowance, which depends upon it is varying from 0.5 degree to 1.5 degree. Now distortion. There are certain surfaces like flat plate, dome, or U shape. It has been observed that after casting even, they are not having the same flat plate or dome or U shape or shape like that, and therefore we need to provide the allowance, so that after solidification, when we take the material out, it may have the shape as we need in the product. Now the shrinkage of metal in mold cavity can be classified into various stages. One is the shrinkage during cooling from superheat to solidification temperature, and then shrinkage during phase change, and also the shrinkage during from solidification temperature to room temperature. Now this is the shrinkage. Now liquid shrinkage, this is liquid shrinkage. Now this liquid shrinkage can be compensated by pouring more and more metal during, or making a feeding mechanism, so that when solidification takes place, then liquid metal may flow in the cavity. But after solidification, there is no way to induce to feed metal. The outer surface of the cavity has got solidified. Therefore, we need to incorporate the shrinkage after solidification from melting point to from melting point to the room temperature, solidification temperature to room temperature. That is to be incorporated in the pattern itself, and that has to be taken into account in the pattern. Now, therefore, there are different volumetric solidification, contraction or expansion for various metals given in this table. For aluminum, zinc, aluminum alloy, white iron, copper, brass, magnesium, carbon, and lead. But there are certain metals which expand after solidification, like bismuth, silicon, grey cast iron, etc., etc. Therefore, we know the coefficient. We can incorporate this thing in the pattern itself. Now, therefore, let us design a pattern. Now, so this is a cuboid, and therefore this is having a length of say L, base of B, and there is a thorough hole of D, and therefore we know the volumetric solid shrinkage, and liquid solid shrinkage. But here in the pattern, we are concerned about solid shrinkage. This shrinkage will take place after solidification. That is to be incorporated in the pattern itself. When we design a pattern, we have to incorporate this volumetric shrinkage, because that can't be fed as in liquid form. After solidification, the pattern, the molten metal in the cavity will get solidified, and therefore it won't get induced. It can't be fed into the cavity, and therefore that is to be incorporated. The size of the pattern should be so much, or the size of the cavity should be so much, that it, after coming to the room temperature, it gains the size we need, and therefore the volumetric solid shrinkage, it is volumetric, and therefore, but we want to measure it in linear direction, and we know that this y, the volumetric one, is 3 times of the solid shrinkage, and hence the length of the pattern will be this much, 1 plus x into L. This will give the length, and similarly we can calculate the weight, we can calculate the diameter, because the metal will shrink, not the cavity. Cavity won't shrink, but the metal will shrink, and therefore we have to give the diameter of the hole such that if this after shrinkage of the metal, around the hole may give the size of the hole at room temperature, and therefore we have to reduce the hole of the pattern by and then after shrinkage it will gain the size, the hole will gain the size as we need, as we desire, and therefore this amount is to be reduced from the diameter. Now there are different types of material being used for making pattern. Say wood, it can be pine, mahogany, teak, shisham, kail, etc. Devdar, or can be metal like aluminium, brass, white metal, cast iron, or say can be quick setting compound, gypsum, and can be wax. Now wax pattern, that they are the parts of the pattern that are fabricated, heated, and the surfaces are joined by heating the surface. Similarly, we can have plastic pattern, like foam, polystyrene. They can be fabricated in different parts and can be joined by using carbon tetrachloride. Now, while making a metallic pattern, we need a pattern. Now, because we can't make we can cast a metallic pattern. Now, to cast a metallic pattern, we need a pattern which should have the shrinkage, the allowances, so that after solidification they get the size of the pattern, that of aluminium suppose, and therefore this allowance should be incorporated in the, while making a pattern we need a master pattern. That master pattern will have the allowance of the metal, pouring metal of the product, as well as the allowances of the metal which we are of which we make the pattern or pattern material. Metal of the pattern may be aluminium, brass, or what metal, what or what not. Therefore, we have to incorporate in master pattern the allowances of the metal of the pattern also. Now, this pattern are also to be, the surfaces of the pattern is to be recognized, so that we can, during fabrication and during the use of the pattern, we can able to visualize, locate the surfaces and handle it accordingly. Now, therefore, say red and orange color is to be coded if the surface is needed as cast. Yellow surface to be the location where we want to machine. Similarly, if we want to have an unmachined opening, then it is black, or like core print, do not want to go for machining, and therefore that can be black on core print. A yellow strip on core print, that gives machined opening. Similarly, green on the sheet, loose piece or loose core print, we apply this green, which we generally for the core sheets. Now, diagonal strips with clear varnish, wherever there is a suppose thin section, wherever we want strengthening, and therefore there we shorten, we need to have this type of painting, so that we can recognize the surface that location needs strengthening. Now, therefore, the tools of the pattern. Now, we generally use this saw machine for wood, lathe machine, planer machine, sandpaper machine, drill machine, files, chisels, tri-squares, dividers, calipers, bevel protectors, hammers, mailer, pieces. These are some, and there can be some more depending upon the requirement. There are few. This is listed a few. But now we are having the technology has got advanced, and therefore there are certain development in making pattern, and therefore we are now using additive manufacturing to fabricate a pattern. Similarly, can be rapid prototype technique, or can be 3D printing, or can be selective laser sintering or stereolithography, or can be limited object manufacturing technique, fuel deposition modeling, laser engineering, nuts, etc. There are the few techniques which has already developed, and we can use all these techniques, any of it, to make a pattern. Now, in pattern, if you want to develop a core element which is having internal cavity in the casting, therefore we need a device to develop internal casting in the pattern. Now, suppose this is the drag, this is the cope, and this is the required object. This is the required object. Now, in this object, in this product, we need a hole. We need a hole. Now, this, if we do not provide any mechanism, then this will be a solid piece, and we want to have the hole. We need to drill a hole. Therefore, instead of drilling a hole, why not to put an element which we call core. This is the core. That is of sand, maybe of sand. Now, if there is sand, then metal won't fill this particular location, and therefore after shake out, we can shake out this core also, and therefore we can have the cavity. Now, this element, that of molding sand, is known as core, and therefore this is to be incorporated, is to be assembled. While assembling the mold, we have to locate and install this core in the cavity itself, and therefore we need to design what should be the size of the core, so that the hole that we need in the product, that of desired dimension. Now, therefore, suppose this is a job, a cylindrical job with the flange, having a hole, a thorough hole, having a thorough hole. This is the side. This is a side view. Now, this is the vertical surface. This is the vertical surface. This is a cylindrical one, but this is the vertical surface. 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 Vertical surface, and therefore, see, a draft is being provided over here. A draft is being provided. This is a draft. But we need, now, to make a hole, we need a core. We need to install a core in the cavity itself. Now, to hold this core in the sand, we need to provide certain support. We need to provide a support in the mold itself. We need to, now, to have the support, we need to provide a passage. Now, therefore, this is a extended portion, both sides, is known as, this is known as core print. Therefore, this is whole maybe a single piece or split type. This is whole one is a solid piece, No, the whole is not there. It is a solid piece. It is a solid piece, and there is a whole. There is a core print on the two end. These core prints are provided to give a passage in the hole, in the cavity. These prints, the core prints are provided to provide passage in the mold cavity, so that can be used to install the core, to give the support to the core. And therefore, actually, if this is the mold and this is the cavity, after making this cavity, the core is to be installed, and therefore this core print has given this passage. Due to this core print, this passage and this passage are obtained. The passage on the both ends were obtained. Now, with the help of this passage, the core is being installed in the cavity itself. Now, therefore, this passage. Now, this size is not of pattern, but the extended of the core is being fabricated, so that it can be used to install, to support the core. Now, therefore, we need to make a core with the help of core box. Now, this is a core, split type core box. We need a core. That core, the size of the core is that with the extended portion on the both end, core print we know, then that is to be incorporated. That length is also to be incorporated. The total length is that of the distance we need, and plus the length of the core print of the both sides. Now, this is another example of a typical core box, split type core box. Now, if we are having this type of core, we need this type of core, but we are having a typical one, very beautiful core box to look. Now, core boxes can be made from wood, plastic, or can be metallic. Sand mixed with binder is packed into the core and then removed. They are baked to harden, and sometimes core are coated with cold wash when there is a high resistant material, often graphite, so that the surface of the core may not react with the molten metal. Core are vented with tubes, so that if there is any gas formed in the core, that can be stripped off, given passage, so that it can be vent out after pouring the metal. If the core is not able to withstand the pressure of the molten metal, then we need reinforcement. It is to be properly reinforced or strengthened, so that it can withstand the buoyancy forces of the moving molten metal in the cavity. Now, there was the force acting on the core, as shown in the previous slide, that is buoyancy force, and can be given by this equation. This is the weight density of the molten metal, this is the weight density of the core material, and we multiply it with the volume of the core. That gives the buoyancy force acting on the core. And therefore, it can also be this force can also be acted by acting on the core, can also be calculated by using a simple empirical formula given by the researchers, where A is the area of the core print and D is the diameter of the horizontal cylindrical core, and therefore we can calculate what is the buoyancy force. That's an empirical relation, simple empirical relation. Now, the this binding force on the core will cause the force to dislodge, misalign the core. Therefore, this force on the core will act on the mold cavity wall of the mold cavity, and therefore the wall of the mold cavity should be strong enough to withstand these forces, and therefore if we look into that, can be given by Fc is equal to dl, strength of the core, where Fc is the acting force on the wall of the mold cavity due to the core. D is the diameter of the core print, L is the total length of the core print, and S is the compressive strength of the molding sand, which comes out to be 45 to 55 kilopascal for steel casting. And therefore, now we know the diameter of the core. Suppose it can be the diameter of the hole we need, and L is the length of the core print. Therefore, we know the diameter. This is the buoyancy force, and therefore we can equate it with the buoyancy force, and we know the strength of the molding sand, and therefore we can calculate the total length of the core print. If it is a divided core print, as seen divided into two halves, then we can have the length of one half of the core print. Now we know the liquid density of few metal given over here, and you can use this density to calculate the buoyancy force, band force on the core. Now there are different types of core according to the composition. Can be green sand core, can be dry sand core, oil sand core, loam sand core, or metal core. Can be metal core, that is to be taken out or can be drilled out after having after shake out of the product, or according to the horizontal, according to the position. Can be vertical one, can be a horizontal one, can be a balanced one, can be a cover type, can be a hanging core, or can be a wing core. Now therefore we have to make a core by using different types of different core boxes. There are different types of core boxes. Can be a half core box, or can be a dump core box, split core box, stickle core box, gang core box. Now this is a half core box. We make half of the core and assemble them together to have the whole core surface, or can be a dump core box. The full core can be made in one box, or can be the split type. We make them together, we pack them as we have seen earlier, and thus we can have the core. Or can be a core when we in one box we are having a number of spaces to make a number of cores. Therefore this type of known as gang core box, or stickle core box when there is the shape is irregular. Therefore what we do, desired shape can be obtained. We fill the core box with the sand, we pack them, ram them, and with the help of a stickle piece of wood, we strike the excess material out, and then we can have the contour of the core as over here. Now this is the core box filled with sand, and trickle out the excess material. Now we can have the desired core. Now chaplets. Chaplets are nothing but metallic supports used to support large and odd shaped cores. We are having cores. We want to assemble this core in the cavity. Well and very good if it can be supported by using this core print and the core sheet. Core sheet is the location obtained by using this core print, the cavity, the space made by core print in the cavity. This extended core print makes some space in the cavity, that is known as core state. Now, if it is large and odd shape, very difficult to give full support, say overhanging, as we seen earlier in the figure. Therefore, we need to have some support, and therefore that can be given, but that can be done by using chaplets. Now, placed in the mold between mold face and the core. Now, this is the chaplet. Now, this is the overhanging core, a cantilever type. Now, this is the cavity. This is the mold cavity. Now, therefore, with the help of this chaplet, they are properly aligned at the desired location. This is a metallic one. As the metal will be poured into it, metal will flow, and it will also surround not only the core but also the core print, and therefore and it will, after solidification, it will get dissolved in the molten metal and will solidify, and therefore generally chaplet is made of that same material, that of the molten metal, so that after solidification it gets consumed in the metal itself, molten metal itself, and therefore this is a chaplet. There are different types of chaplets depending upon a requirement. We can use any type of chaplet. Now, the forces will also act. We fill the mold cavity with molten metal. Now, the whole surface of the molten metal will apply band force on the cope, upper flask, and therefore let us see what should be the total band force which is acting on the upper flask, that is scope of the molding flask, and that can be given by this equation. This is the force, band force, that depends upon the area of the cavity and the weight density of the metal, and this is the head of the metal, and this is the height of the cavity in the cope, and that gives the total band force acting on the cope. Okay. Now, if this band force is more than the weight of the cope, then proper clamping or weight is required on the cope. Otherwise, it will lift the cope and the molten metal will flow out. Therefore, we need a proper weight or clamping of the flask, so that it may not lift, this band force may not lift the cope, and therefore that is to be calculated and accordingly. Thanks for hearing. This is all about the design of the